In this video, we are going to concentrate on corrosion kinetics part 3. And the outline of this part 3 kinetics is that we're going to study the anodic and the cathodic polarization, the Evans diagram, and corrosion potential and corrosion rate. Now, let's look at the cell for measuring corrosion potential stat or galvanostat. And when we talk about the corrosion potential stat, it's a setup that is used to find the radius potential reaction and also find the reversibility of what a reaction. Now with these setups, you have some part in which you need to understand the part. We have a voltmeter, and what does this voltmeter does in this setup? The voltmeter is used to find the what potential difference. That's what the voltmeter does. And also we have the ammeter. The ammeter is for current, right? So for current passing through this setup. Let's look at the type of electrodes that we have here. Let's first tackle the working electrode. Now, the working electrode, when we talk about the working electrode, right? The working electrodes form part, an important part of the what? The potential stat. And it serves as what? A site where electrochemical reaction of interest occur. And the function of the working electrode is to facilitate the transfer of what? Electron between the electrode surface and the species in the solution. So the species in the solution and the what? The electrode what? Surface. Transfer of what? Electrons, right? Let's look at the reference electrode. When we talk about the reference electrode in the potential stat, it's serves as a stable reference point for measuring what? Potential of a working what? Electrode. It maintains what? A constant and a known potential. Are you getting it? So it helps maintain a constant and a known potential. So this is the reference electrode, and this is the working electrode. And the reference electrode, we have some reference electrode. We have the silver chloride, we have the standard hydrogen electrode, and we have other. But the most common one is the silver chloride, and I think standard hydrogen electrode. Now let's look at the counter electrode. So when we talk about the counter electrode, it's also known as the auxiliary electrode, and it completes the what? Electrical circuit in what? A potential stat. And its function is to provide what? A pathway for the flow of what? Electrical what? Current during the what? Electrochemical measuring or the electrochemical measurements. Let's move on. That is what you need to know about this. Now, there are some questions for us to answer here, which is very important. So from the potential stat, what is the control and the measured variable in a potential stat? So now for the control, let's look at the control A. So for question number 1, the action of the control. For the control, so for the control variable in a potential stat is what? The cell potential, right? The cell potential, which is the voltage difference. Are you getting it? Yeah, the voltage, which is the controlled variable. And with the measured variable, when you talk about the measured variable in a potential stat, it is the cell current, right? So we measure the cell current. And the second question was is which of the electrode can these variables be controlled and how and measured? So for controlled, we know that, let's go to the for the controlled, we know that this is for the control, which is the potential, the cell potential, right? The cell potential. And we are talking about which electrodes. Let's look at the question again. Which of the electrode can these variables be controlled or measured? So for the controlled, the electrode is between what? So for the controlled, the cell potential, let's look at the cell potential. So we have it to between this electrode, which is the working electrode, and what? The reference electrode. So for the potential difference, which is a controlled variable, is determined between the working electrode and the reference electrode. And let's look at the measured one. This is the measured one, which is for the cell current. And for the cell current is measured between the working electrode. So it's measured between the working electrode and the counter electrode. Because the counter electrode what? Help flow of what? Electrical what? Current. So we should note that. So for the second question, for potential, cell potential, we have that it is the working electrode and the what? the reference electrode, and for the measured, which is the cell current, we have the working electrode and the counter electrode. Let's take note of. Let's move on to measuring of corrosion rate. So for measure of corrosion rate, right, we have two measure of corrosion rate, which is the linear polarization and the Tafel extrapolation for uniform corrosion rate measurement. Let's look at that. This is for uniform corrosion measurement, and we have the potential dynamic and the cyclic polarization measurement for what? Corrosion behaviors and mechanism. And this is for localized form of what? Corrosion. Let's take note of that very well. Now, when we talk about open cell potential, what does it mean? You know, in applied electricity, we know that open voltage, we have open current and closed current. Open current is that there's no current flowing through, right? It's open. So the potential at which no current flows, and it's also known as what? The equilibrium potential. The equilibrium potential. So now let's digest the linear polarization resistance from the linear polarization, right? So the linear polarization resistance is that you are going to find, we have a linear line which you are plotting against the E against the I. So the current density against the what? The potential. Are you getting it? And then we are supposed to find the polarization resistance, and with that, you're going to help us to find the I core. So with this, we need to attain a value from here, and from the value we can decide to find the I core. So the value we are supposed to find RP, which we will use for calculation, which is the polarization resistance, and that is the change in the E over the change in what? Current density. So this is a linear, this one graph. So we find the gradient, which will give us the change in E over change in I, and we are going to get the polarization resistance, right? So you say, what is the corrosion current for steel alloy exposed to a corrosive environment? The linear polarization curve measured in the environment is shown. So we are going to use one to solve. So this is it. This is the linear polarization curve, and we are supposed to find the corrosion rate. So for here, this is a curve way. So we look at the linear side. So from this side, we can draw a linear side, which will give us this straight line. That's why I have this linear. And from here, we can attain our gradient, right? For here, we can attain our gradient. And with this one, they use this. I think they drew this and they use this. So therefore, they find the change in E all over change in I. And that give us the polarization resistance, linear polarization resistance, and they had it to be what? 2.2 volt ampere, right? And then we assume that the Tafel constant of the anodic reaction is equal to the Tafel constant in the what? Cathodic reaction, which is 100 millivolt. So we are supposed to determine our what? Our B. And for us to find the I core formula, I core is equal to this B over what? The linear polarization resistance, right? Now we know how to find the linear polarization resistance from the graph given to us. But the B, for us to find the B, there's a formula for the B. So for us to find the B is equal to the Tafel constant at the anodic times the Tafel constant in the cathodic all over 2.303 Tafel constant in anodic plus what? The Tafel constant in what? Cathodic action. So with this, note that this, we assume that the Tafel constant in the anodic is equal to there's no negative in this one. Let's note that. Don't let it confuse you. So from there, you do substitution. And when you do substitution, what you're going to get is that you're going to get, let me write the substitution. You're going to get our B is equal to 100 times 10 exponent negative 3 times 100 times 10 exponent negative 3 all over 2.303 100 times 10 exponent negative 3 plus 100 times 10 exponent negative 3. You close the bracket, and at the end, when you do that, what you're going to get is, when you do that with your calculator, you're going to get an answer which is approximately 0.022 volts. And for us to find the I core is what? The B all over the linear polarization resistance, and the B was given to us as 0.002, then divided by the linear polarization resistance obtained from the graph. We had it to be what? 2.2, and at the end, our I core will be giving us 0.01 amps per meter square. This is how we use the linear polarization. Fine. Now let's look at the Tafel extrapolation. Our previous video, we've talked about Tafel equation, right? So for here, you know that in activation polarization, we will get it's a linear relationship. But in this case, this graph is not linear. So what you do now is that you draw a line which is what? Tangent to this. So you draw a straight line which is tangent to this, a straight line which is tangent to pass here. And also you draw a straight line which is tangent to this line, to this curve, so tangent to it. And then where they intersect, you trace this from here. So when you trace this become our what? E core, and here become our what? Our I core. But note here, this is in what? Log I. So the value that you get here, you're going to like log I is equal to the value, and then you find the antilog of it, and you get the answer. For example, if the value here is what? Let's assume that it is 4.7. So we had our log I is equal to 4.7. So what will be I? So I is equal to 10 exponent 4.7, which the I is the I core. So 10 exponent negative positive 7, positive 4.7. That will give us our I, which is the I core. And our E core can be measured from here. Are you getting it? That's it. So using the Tafel extrapolation, you have the graph, with this one represent the anodic over potential, and this is the cathodic over potential. But you draw a line which is tangent to the graph, tangent to the curve, and then where they intersect, you trace down. This is the I core and this is the E core. That is for the Tafel extrapolation. Let's look at the potential dynamic and the cyclic polarization, which is for the localized corrosion. So for the potential dynamics, now let's look at this question. Ion water system showing the effect of potential in a moving system from a corrosive, that is active region 0.1. Where is 0.1? This active region 0.1 to a passive region, which is 0.2. Is a passive region. Now note, under certain conditions, right, of potential and what? The pH, some metals from the protective layer. You've done that in the thermodynamics, corrosion thermodynamics, right? And we can examine the kinetic using a potential dynamic scan and Evans diagram. So potential dynamics scan, Evans diagram. The Evans diagram is the E against the log I. Now, but what I didn't say is that for the linear polarization, right? For linear polarization, the voltage, the applied voltage for the linear polarization, let's note that it is what? Plus or minus 10 millivolts. Let's take note of that. And for the potential dynamics, the applied voltage, I want you to know that the applied voltage is beyond 10 millivolts. So for the anodic side, we have plus 150 millivolts, and for the cathodic side is negative 20 millivolts. Let's take note of that. So now we talk about the potential dynamics polarization method, and what does it do? You see, it's from here we can examine the kinetics of this reaction using a potential dynamic scan or the Evans diagram. So here we have that the potential dynamic polarization, what does it do? It's used to produce a quantitative picture of what a substance in a given solution, and collaborate in rapidly identifying desirable material environment combination, and in predicting how the material will behave when exposed to a particular environment. And also it detects important information such as the potential region over which the specimen remains passive, the corrosion rate in the passive region, and the ability of a specimen to spontaneously passivate in a particular medium. So that is what the potential dynamic polarization means. So it's going to give you a graph which is E against log I, and giving you at what potential will the in the reaction will that substance passivate in that solution, which reaction will undergo active, and also will show the transpassive region and rate. So let's look at the potential dynamic scan. When we look at the potential dynamic scan, have on this side, this is the potential. We are using the saturated calomel electrode as the reference electrode. We have the log I, which is the log of the current density, milliamps per squared. So we have this, which is the scan. After the scan, let's describe it. So Above this, we have that water is breaking out to give oxygen as 4H as plus electron, wherever is what oxygen what evolution. When we start from here, we have this being the anodic and this the cathodic, right? In the TAFO extrapolation, we know that, or the TAFO extrapolation, we know that we have this and one graph is going here. In activation polarization, because it's linear, we have it to be this. Here's activation polarization, right? And it goes here and it comes here. The same thing applies here. So in this case, the metal undergo passivation, repassivation, secondary passivation. So this is the cathodic, whereby it's negative. So this can be what potential of EC, and this is what this over what A. So when it's going right, and the cathodic, depending on the the potential applied in the material, you'll be able to know whether the material will undergo passivation or active. You know the active region, the passivation region, and the transpassive region, and you know how to control and help control corrosion. That one too can be applied in that. So now, when you see a line like this, you see this curve, some small curve. It represents the passivation, the passive region. So from here, this is what the passive region. So between this and this potentials, you get a passive region of the ion in water. And as it goes on, we have the transpassive region, and then we'll go to the secondary passivity and then move on. And here from this side to this side is the what? The active region. And the current for this one, that's the current density for this, is called the what? I critical. That's the critical current. We should also know that the EP, that's IP, is the passive current density. The passive current density is this side. So the current obtained from here is what? The passive current density. We should know that. And let's move on to a question. So there's a question I obtained from online, and this question is asking us to label the part, right? So let's take this. We should label the part. Now we already know that for our A, we know that this A represents what? The active region. So this becomes the active region. And there's the potential against the current density. That's the log scale. And then our B, what will be our B? When you see something like this, it tells you that is what? The passive region. So this becomes the passive region. And this side is the transpassive region. You can see it, transpassive region. Let's go back to this one. We know that this side is what they drew. From here, they drew this side, and then they came here and they moved down here. They came. So this is the transpassive region. So this side becomes the transpassive region. That is for C. Now let's go to D. What to be D? What is the this one? The name of D. So when we talk about D, our D becomes what? This becomes the critical, right? That is the critical current. This is the critical current density, the critical I critical. From this one, you can know that this is what? I critical. From here, this is I critical. Knowing how to label it is very important. This is a question I obtained from online. And let's go to our E. Our E, we know that is a passive current density. That is ICD, passive current density. The passive, our E is what? The passive current density. And then when you go to our F is the what? The primary passivation potential. There's a primary passivation potential. I always term at PPP, EPP, primary passivation potential. And this is the projection potential. And our the E here becomes the what? The passive current density. And on the passive current density, the potential of the passive current density is what? The protection what? Potential. And our EF represents what? The PPP, the primary passivation potential. That is this. There's the question I obtained online. They say we should label the part. Now let's move on. Now let's talk about the potential dynamic. Now the potential dynamic at which the current becomes virtually independent of the potential and remains virtually stationary is called the flat potential. So when you look at the diagram, this is the flat potential. We have something like the flat potential, right? So FE, the flat potential, and this becomes the what? The IP. That is the current density. That's the passive current density. Let's look at that. And then the minimum current density required to maintain the metal in a passive state is called the passive current density. So this is the passive current density. This current here is the passive current. So when you trace this to come down here, the current that you get here is the passive current density. But let's note that this is in what? The log scale. So whatever you do, you find the anti-log of it, and that will give you the answer. Move on. Now let's look at the cyclic pattern scan. So we have to, I told you that for the localized this one, measuring the correlation rate, we have the cyclic and the potential dynamic, right? So that we've talked about the potential dynamic, and we are looking at the cyclic pattern scan also. That's for pattern corrosion. So in this case, this scan will let us know whether corrosion occur or not. So we have the E protected, we have the protection potential. We said that in the question that we have protection potential. This is the protection potential. We have the protection potential, and we have the E-pit, the protection, that's the pitting potential. So at that potential, there's relationship between the pitting potential and the protected potential. Let's look at this. If the pitting potential is equal to what? The protection potential, there will be little tendency to pitting. So I want to draw, let me change the color from here. Now, with this is a loop. You can see that it goes here and there's a loop here. The larger the loop, the higher the rate of corrosion. So for the first one, for you to draw the cyclic pitting on a cyclic pitting scan, you know that E pit is equal to E pro. That means that they will be on the same line. So this side, the loop will be very small. So they will be on the same line, right? They will be on the same line. That means that there will be little tendency to pattern, right? Corrosion. And if the E pit is less than the E pro, that means that the pitting potential is less than the protected potential. That means that there will be no tendency to what? Corrosion. So there will be no tendency. So therefore, the loop, how the loop will be like, it goes here and then it will come back to this side. I get it. So there will be no corrosion. But if E pit, that's the pitting potential, is greater than the protected potential, that means that corrosion occur, and that one the loop is very big. So it goes like this. You have a bigger loop. That is, the loop is like this, and this means that corrosion, that's pitting corrosion. Okay, let's take note of these three.